deep into the earth, searching for water, oil, and knowledge. Grinding, crushing, and scraping the way through earth, steel, ice, or stone. Now, drilling on Modern Marvels. The New Mexico desert. This may seem an unlikely place to drill for water, but that's precisely what the EADS drilling team is here to do.
Level the rig up good and straight. That way, when we're drilling, we maintain a level hole. We're not getting crooked and causing a problem.
With his rig set up, Alan EADS lowers the first of the many drill bits into place and starts breaking ground. Water well drilling is a $3 billion a year industry. In the United States alone, water drillers create 800,000 new wells annually. When they drill, they usually find water. You can't tell by looking at the surface, but this semi-arid region sits atop one of the largest aquifers, or underground water reserves, in the United States. The 174,000 square mile Ogallala Aquifer. This puts the odds of striking water in the EADS team's favor. They'll have to clear approximately 6 feet of topsoil, 100 feet of various limestone and sandstone rock, and 10 or more feet of sand before they can expect to reach the water table. Within 20 minutes of drilling, the team hits rock, and it's time to change out the drill bit.
This is our downhole hammer. It's run off the air compressor of the drilling rig. It's an 8-inch bit. It'll cut rock a lot faster than any other method. It has sped the industry up tremendously in hard rock drilling.
This downhole hammer works by thrusting into the rock up to 1,500 times per minute as the drill string, or drill pipe, is rotating.
Pretty much it's a one-man operation during the drilling process, once you get set up.
The EADS team's drilling rig has come a long way from the earliest well drilling, done in ancient China around 600 BC.
They use a method of percussion drilling that they called a spring pole. A spring pole is just simply a branch or a tree itself with a fulcrum, like a teeter-totter. But they put the fulcrum on closer to one end so that the other end stuck up high in the air. And then they produce a reciprocating motion that raised and lowered the bit. And that pulverized the formation.
Lagging behind, Europeans were still digging their wells by hand until 1100 AD.
There were a number of wells drilled in Western Europe after the first millennium, and some of them were very deep. They used primitive percussion methods. A famous one at Artois in France was drilled in the 11th century. It went over 1,000 feet deep.
Famed 15th century artist and inventor Leonardo da Vinci sketched a design for a radically different well drilling apparatus. The principle was simple. It used a sharp rotating bit to delve into the earth. But it wasn't until the mid-19th century that rotary drilling became a viable option for drilling deep wells.
In the 1840s in England, they had the idea they would circulate fluid down, and as they circulated the fluid, they would bring the rocks back out. The advantage of being continuous as opposed to a batch process. And so your efficiencies went way up.
Rotary drilling is the method used to drill 85% of all deep wells in the United States, including this one, being drilled by the EADS team. They sometimes employ a percussive element, like the downhole hammer. 1 hour into the drilling, they've passed the rock layer and changed the drill bit once again.
This is our drill collar we run in when our final trip to go to bottom.
The drill collar consists of a drill bit attached to a weighted pipe.
This drill collar weighs approximately 1,800 pounds. It just more weight on the bottom of the string, drill string, keeps the hole straight. Ready? We got to add more pipe to get deeper. Our carousel with our pipe rack over on the side, we can go up to 300 feet with what pipe we carry on the rig. Our deepest wells here are around 250 to 260 feet. Don't want that. That's 7696.
Now that they're drilling into sand, they introduce a special water polymer mixture. The mixture is pumped through the drill bit and into the hole. The mud created forces the cuttings up to the surface and also stabilizes the well.
That's the water sand we just hit. Started the rattling and getting into gravel. It's just a lot coarser sand. We hit it probably at about 110 feet. But I think this is going to be a good well hitting it that shallow.
Not even an hour and a half into the drilling, and they hit the water table. But Alan still needs to continue to drill for another 100 feet or so, until he hits the bottom of the aquifer.
The last 10 years, probably 80% of our work has been replacing wells that weren't drilled all the way to the bottom of the aquifer. The aquifers just slowly dropped in level, and those wells have started going dry. So now nearly all the new wells we do, we go to the bottom of the aquifer.
3.5 hours into the operation and approaching 225 feet, the drillers anticipate hitting the bottom at any moment.
That rig plays the bottom of the aquifer now. We'll start flushing the hole out, see if we get some clear water. There we go. We have water. Nice and clean.
Water well drilling, brine drilling, and so forth is obviously very critical to humanity. We need water. But oil is one of those commodities that people are willing to pay a lot for, obviously. And so, if you will, the money follows where that is. And so, if you will, the technology is in the oil and gas industry because that's where you can afford to do the research and the development of the various tools that we use to develop and drill wells.
Today's oil well drilling is a long way from the early days, when second-hand water well technology was used to drill for crude. We now return to drilling on Modern Marvels. In the Gulf of Mexico resides one of the world's largest and most sophisticated drill rigs. Its mission? To tap into oil deposits created by decaying life forms that populated the region 200 million years ago. Deposits potentially buried hundreds of feet beneath the seafloor. The Discoverer Deep Seas is a fifth-generation floating drilling rig, or actually, a drill ship. It's 835 feet long and 125 feet wide, and boasts not one, but two drill systems in a single derrick.
As this rig floats on the sea, we can drill in 10,000-foot water depth. So that means basically we've got 10,000 feet of water before we ever get to ground and ever actually get to break ground with a drill bit.
The Deep Seas utilizes the most up-to-date rotary drilling technology in the world.
Right now, we're drilling an 18 1/8 inch hole. As you can see, the drill string right here is rotating. As the drill string rotates, it rotates the bit down the hole, anywhere between 150 and 200 rotations per minute. Right here we have what we call a PRS. It's a pipe racking system. And this is the mechanization that you see on board an offshore rig that you don't see on a typical land operation. The PRS will come in and pick up a piece of drill pipe. It'll move it over and stab it in. No people actually need to touch this equipment.
From the 135-foot-long drill string assemblies to the 226-foot-tall derrick, everything on this drill rig is bigger and better, including the drill bits themselves.
We've got two different types of bits here. This is a tri-cone bit, sometimes called a roller cone bit. This bit, as you can see, each of these cones individually moves. But the way this bit will drill is you'll run it on the bottom of the drill string. As it sits down on the formation and you start rotating the drill pipe, these tend to move around as it rolls around, and it rolls around and actually breaks up the formation.
The father of an American icon developed the roller cone bit early in the 20th century.
A guy named by the name of Howard Hughes Sr. came up with that in 1908. And what he did is he actually only had two. The tricone actually didn't develop until about early 1930s.
The newest drilling bits are called polycrystalline diamond cutter bits, or PDCs.
Out here in deep water, we typically use the more expensive PDC bits. The PDC bit, the way it cuts is through dragging or a scraping or a scouring action. And you can actually see the type of cuttings that it will bring up, as you can see as it scrapes around the bottom of the hole. Here you can see where the nozzles are. The nozzles are what actually transports the drilling fluid out from the drill string. It'll come around and come down through these channels. And these nozzles are actually sized depending on the application.
Today, drillers are no longer committed to drilling a vertical hole.
Chevron right now is paying about $500,000 a day to be out here drilling. In order to maximize that and get to our target quickly and efficiently, we use high-tech tools. One of the tools we use is called a rotary steerable system. For a rotary steerable system, what it allows us to do is to be able to rotate the drill string and change direction in the hole at the same time. And as this thing is rotating, those pads will pop out as the drill string moves, and as you want to try to nudge the bit to the left or to the right to be able to build angle to get to our target.
To determine where to drill, the Chevron team members are armed with the latest in seismic 3D technology. Hundreds of miles away in Houston, they have an extended network of geologists and engineers at their beck and call. And 10,000 feet underwater, they have remote-operated vehicles, giving them a glimpse of what's happening on the seafloor. But even with all of these high-tech tools, striking oil remains hit or miss. Still, with all the technology found aboard the deep seas, the cards are definitely stacked in their favor. We now return to drilling on Modern Marvels. At the Japanese port of Nagasaki, the largest and most sophisticated of all scientific drill ships has recently been unveiled. It's called the Chikyu.
It's 660 feet long, more than 2 football fields in length. It's got a drilling derrick on board that's the tallest derrick in the world. It's something like 370 feet high above the water line. That's taller than the Statue of Liberty.
The mammoth 57,500-ton vessel dwarfs all other rigs used in scientific exploration. When fully assembled, the drill pipe is nearly 6 miles long, about 22 times the height of the Empire State Building.
The Chikyu is the latest incarnation of scientific ocean drilling vessel, and it's designed to be able to drill as much as 4 or 5 miles beneath the seafloor in order to get at parts of the Earth's crust, the plate tectonics, and the upper part of the Earth's mantle that we've never been able to drill into before. So we can study whole regions of the Earth that we really never have had access to until this ship came along.
The Earth's mantle is truly virgin territory.
One of the fundamental boundaries in the planet is the difference between the crust and the mantle. And we call that boundary between the two the moho layer. The moho is just that boundary between the rocks of the crust and the rocks of the Earth's mantle, which makes up something like 2/3 of the planet. No one's ever taken a direct sample of the mantle of the Earth. So the ability to get there and study what those rocks are like is an important goal for Earth scientists.
The Chikyu won't be the first drill ship to attempt this Herculean task.
The first project, actually, that started scientific ocean drilling in 1963 or so, called Project Mohole. And the idea of that project was to go out into the ocean and actually drill through the Earth's crust and all the way into the mantle of the Earth. They severely underestimated how hard this was going to be, and they failed to actually get to the Earth's mantle.
To reach the great depth of the Moho layer, the GQ is drilling in the middle of the ocean, where the Earth's crust is thinnest. And it's taking notes from the oil industry by incorporating a riser in the drilling process. The riser extends around the drill pipe from the ship to the sea floor. This shaft allows drilling mud to flush all the cuttings back up to the ship, shoring up unstable sediments and keeping the borehole clear.
Prior to this, without a riser system, scientific ocean drilling has always been done just with the drill string itself cutting the hole. Seawater is pumped down the drill string to flush the pieces of rock out of the hole, and they just pile up on the seafloor. That works fine for drilling, several thousand feet, but as you get deeper and deeper, it gets harder and harder to maintain the hole that way. So to go deeper, we need this riser system. So it can drill 2 or 3, 4 times deeper than we've ever been able to drill in the ocean floor before.
Even if the GQ succeeds in boring to the Moho layer, we will have only begun to scratch the surface, as there's more than 3,000 miles to go in order to reach the Earth's inner core. But as the GQ begins to probe the Earth's crust, other scientific drilling devices are uncovering thousands of years of history through ice coring.
One of the important things about ice coring is that you get a completely continuous record. Because this kind of drilling is done, the surface temperature on the ice sheet never gets up above to the melting point or above. So all the snow that falls stays frozen, it never melts, and it just continues to pile up.
To preserve the integrity of the cores, unique ice coring drill bits are used.
The idea of a core drilling system is to cut an annulus around a pillar of ice. The cutting is done by these knife blades here, which are sharp, and they act just like a carpenter's plane. As the drill rotates, it cuts down into the ice. If you have one piece rotating, you have to have something for it to provide resistance to that rotation. And that's what this anti-torque section does. The anti-torque section, these are springs that I can compress. They extend out and are pressed up against the wall of the hole.
To date, scientists have been able to uncover over 1 million years of climate history through ice coring. But drilling in ice is not limited to core sampling. Scientists are currently constructing a neutrino telescope at the South Pole, requiring them to drill 80 holes, 1.5 miles each, into the ice sheet.
We need to be in ice that's very clear. We want to be in what looks like cocktail ice. So cocktail ice is, if you've ever noticed, it's very clear. There's no cloudy bubbles in it, like the kind of ice that you might make in a tray and then put in your freezer at home. So at the South Pole, due to compression and age and so forth, the ice that's about 1.5 kilometers deep and deeper is, we have found, very clear and very suitable for our experiment. And it's one of the few places on the planet where there's really ice that we can use for this experiment.
The Ice Cube engineers had to find an inexpensive and efficient way to drill a hole through the ice. Their method of choice? Hot water, or more precisely, an enhanced hot water drill.
You just simply cannot drill a straight enough, deep enough, wide enough hole to meet our requirements of a couple feet across and over 1.5 miles deep with a mechanical drill. So then what else do you do? Well, we've all probably had some experience actually melting ice with a water jet. Then in order to increase that efficiency, if you scale that water jet up and heat the water, you could actually very effectively melt ice.
The enhanced hot water drill sprays 190-degree Fahrenheit water, pressurized to nearly 1,000 pounds per square inch, into the frozen path, melting the ice at a rate of over 3.5 feet per minute.
You direct this water through a flexible hose. So we have nearly 10,000 feet of this hose wrapped up on a very enormous hose reel. It's actually a very high-tech device. You just keep unspooling your hose as you go down the hole.
With 200,000 gallons of ice melted per hole, each hole takes approximately 30 hours to drill.
Eventually, because the South Pole ice is very cold, it's going to freeze back. Typically, the holes we drill, so they're a couple of feet across, they will freeze back solid in about 40 hours, more or less.
After the hole is drilled, the Ice Cube team has to work against the clock to get all of their instrumentation installed before the hole disappears. Strings of basketball-sized optical modules will be frozen deep in these holes. The modules will be used to detect neutrinos as they dart through the ice. They might be the key to our discovery of some of the most profound secrets of the universe. In the 1970s, 80s, and 90s, Russia drilled the Kola Super Deep borehole. At more than 7 miles, it's the deepest hole ever drilled. But it failed to reach the Moho layer. Drilling will return on Modern Marvels. We now return to drilling on Modern Marvels. Deep in a West Virginia limestone mine, toils one of the largest tunnel and mining drill rigs in the United States. The Rocket Boomer XL2C Jumbo Drill. Drill rigs like this one are a critical component in drill and blast tunneling. Holes are drilled into the surface, and dynamite is inserted into the holes to blast material from the face of the solid rock.
The Rocket Boomer series of drill rigs can be used in just a wide variety of hard rock mining applications. The machine weighs approximately 90,000 pounds as you see it, and has a reach of about 55 feet wide and about 45 feet high from a single setup.
Double penetration allows the operator to drill 88 holes, 18 feet deep, into solid rock in less than 3 hours.
On the end of the boom, you've got a drill feed, which will be feeding the drill bit in and out, well, in when we're drilling the hole. At the same time, there is a rock drill hammer on that feed, which will be giving an impact movement to the drill itself, and also at the same time, the bit will be rotating.
In just a minute and a half, the drill penetrates 18 feet into solid rock, a length slightly longer than the height of a typical single-story home. From inside an enclosed cabin, the drill operator controls both arms simultaneously, using a pre-programmed computer console to guide his appendages.
He has a joystick in the cabin, just like a video game that you have at home. So you have a joystick, and it will locate that boom to the next hole, and in a precise area and a precise angle that he wants to drill out to. And once he's done that, he'll start the drilling cycle again.
With machinery like this Rocket Boomer, the modern driller's job description is drastically different from that of early 19th century drillers, and the manual drilling process made legendary by John Henry, the steel-driving man.
What we see here is a typical star drill and a couple of sledgehammers. In order to make the hole, one man would hold one of these drills, and either 2 or 3 men would hammer the drill. It was relatively dangerous for the guy holding the drill, but clearly the men that had the sledgehammers were highly experienced, and they didn't break his hand very often, hopefully.
In the mid-1800s, engineers tunneling through Hoosick Mountain in northern Massachusetts were literally breaking new ground.
At the time, the only type of drilling was hand drilling. But the rock at the Hoosick Tunnel was extremely strong. It was a granite type of rock. It was very difficult to drill by hand. And actually, the mechanics in Massachusetts developed a pneumatic drill that was driven by compressed air.
Hoosick Tunnel engineers also introduced a more powerful blasting agent, nitroglycerin, replacing gunpowder to blast the rock face. The Hoosick Tunnel had also been the proving ground for another tunneling innovation. Instead of drilling small diameter holes in the rock for blasting agents, engineers experimented with a primitive tunnel boring machine to drill one tunnel-sized hole.
The steel wasn't strong enough, the power source wasn't powerful enough, but they came up with a concept for using a full-face tunnel boring machine at the Hoosick Tunnel.
The full-face boring machine ground 10 feet into the solid granite of Hoosick Mountain before it died.
And this predated the actual development of these machines by over 100 years. The machines weren't actually ever developed as a practical apparatus until the 1950s. But these gentlemen were trying a similar concept at the Hoosick Tunnel in the 1850s. So they were way ahead of their time.
Today, tunnel boring machines, or TBMs, are standard issue in civil engineering tunneling projects, like this extension of the Los Angeles light rail system.
This tunnel stretch is a 7,000-foot long stretch underneath Boyle Heights. Twin tunnels, 6.5 meter in diameter, 21 feet diameter.
65 feet underground, the tool of choice, or rather tools of choice, are twin tunnel boring machines. The 344-foot long, 1,025-ton beasts are expected to burrow through 50 feet of earth per day.
It basically pushes and digests the ground, but it does it in a controlled manner to make sure that it always maintains a pressure within this cutter head and plenum system, so it's not greater than so it's not less than the ground pressure around it.
Each massive boring machine is equipped with a closed-wheel cutting head that contains 18 tungsten carbide-tipped disc cutters.
Well, this cutter head weighs about 75 tons. It gets turned around and around about 2 RPM, maximum 3 RPM. But really what it does, it can turn both ways. It's one big disc of steel with a bunch of tools on it that dig the material. And what you see on here, the yellow things here are disc cutters. And then you see these openings here and here. These are bucket openings which collect all the material and basically scoop it into the plenum of the cutter head.
As the cutting head rotates, scraping into the ground, it is slowly pushed forward by 32 hydraulic jacks, which exert a total of 1,200 tons of thrust on the head.
Basically, the machine will thrust off the tunnel lining and mine 5 feet, retract jacks in certain locations and start building that liner in the space that we just created. So basically, we push, mine, and then we build a ring, and push, mine, build a ring. There's actually 6 nozzles on this cutter head. They're 2 inches in diameter. And what we pump through there is typically foam.
The foam works essentially the same way as drilling mud. It mixes with the cuttings, making them the ideal consistency to move through huge screws away from the cutter head. At the helm of this giant is an operator who controls these screws and monitors the machine to make sure nothing goes wrong.
I control the screws, I can speed them up, and I can empty that chamber out real fast. I can slow it down and keep that chamber full. If I slow it down, then my advance here, where the machine's gonna slow down. And eventually, if you slow it down too much, you'll just start shoving into the ground, and the ground's gonna go somewhere, it's gonna go up. So then you're gonna create a hill up top. If I speed it up too fast, and I take that material out of the chamber fast, then the ground's gonna come down and we'll have a sinkhole.
Behind the drill head, these screws, or rotary augers, move the muck through the entire length of the machine.
You don't even see the ground that you're mining until it's actually dropping out of the contained screw conveyor all the way at the end, some 200 feet from where it's actually coming out.
Depending on the type of soil, a tunnel boring machine like this one is capable of excavating up to 20,000 tons of material a day. We now return to drilling on Modern Marvels. On the Sea Ray boat's factory floor, laser-guided robots wielding drills are revolutionizing the boating industry. They function as both the drill and the drill operator.
What you see here are 2 ABB IRB 6500 robots mounted on rails, and they run off of one controller.
The robots perform a choreographed drilling sequence, unique to each boat style, maneuvering around the vessel effortlessly.
Yeah, the robots have 6 axes, and also being mounted on this track, that's an additional axis, so it's actually 7 axes. What that allows is a lot of mobility of the arm to articulate in whatever position it needs to. And also with the 7th axis, the robot can travel back and forth and cover a large area and work on a part as large as this.
The robots have 40 horsepower spindles that can turn the carbide drill bits up to 18,000 revolutions per minute. And their precision and accuracy are unparalleled.
The guy doing it by hand, he has to measure everything out, which takes time. He has to make sure he can read the tape measure correctly and get everything laid out to the correct specs. With the robots, we don't have to do that. By hand, on average, it would take about an hour to lay out the boat completely and drill it for all the options. With the setup that we have now, we're doing it in about 20 minutes.
Plus, the robots always show up. They don't need lunch breaks, and they never complain.
It's nice to see the work that you put into it, basically at a desk. And then you come out here and it does everything that you want it to do. For the most part, it's dead on. It's so precise. And you get that consistency that humans can't provide.
Though technically impressive, these robotic drills employ some of the same principles as the earliest hand drills.
Some of the earliest drills that we have are the stone tools of native people. This is an example from early America, several thousand years old, dating to the Archaic period. Basically a stone perforator, pointed, napped to a point, that would have been inserted into a wooden handle, lashed together so that you would, through your hands, spin the tool back and forth and create a hole. And so at its most basic level, that is a drill. A similar kind of tool is the bow drill. Again, a kind of chisel or very simple point mounted on a spindle with a bow that looks a lot like a violin bow. I can't do this exactly because it's impossible with the age of the material to actually twist this around, but with the string on the bow twisted around the cylinder or around the spindle and moving it back and forth would create a spinning motion, a reciprocating spinning motion that would create your hole. The bow drill was known in antiquity. It certainly was a tool that was known to the Egyptians and the Romans, for example. A similar kind of tool is the pump drill, which is also a back and forth reciprocating motion, but relies, instead of pulling it back and forth on the bow, you are pumping up and down.
By the early 15th century, a vastly more powerful hand drill had been developed that allowed for continuous rotary motion. The brace.
Now you have a drill, or more popularly a boring tool, a bit, moving in a constant and single direction. And the way these tools worked is that they relied on interchangeable pads, or chucks we might call them today, in which one could insert a variety of sizes of bits.
By the time the brace had made its appearance in the tradesman's kit, the bit itself assumed many shapes and sizes.
The big advance with drilling, or more properly boring technology, was the innovation of the twist or spiral bit. With the screw, not only do you bore that hole, but you also have the additional advantage of the screw carrying the shavings back up and out of the holes.
Drilling technology took a giant leap forward in 1895, when a radical new hand drill, invented by Wilhelm Fein in Stuttgart, Germany, came on the scene.
It was the first electric drill, and though it probably weighs 10 to 12 pounds or so, it was real easy to use for the average person who wasn't having to hand crank that bit and brace all the time. It did get kind of tired in the hands. It was a bit ungainly, but it was real easy for the average person to be able to get behind it, to actually put his chest on here and actually push into the work.
In the early 20th century, Black & Decker made the portable electric hand drill even easier to use.
So along came a couple of guys named Duncan Black and Alonzo Decker, and they had this brilliant idea that they got from the Colt 45 pistol, the pistol grip. And right here is, I mean, this is very much like the original Black & Decker power drill, which came out. They actually came up with the idea in 1914. They took it to market in 1916. In 1919, they took a van around the country and they went to hardware stores everywhere and they demonstrated these things and people were just amazed.
Their invention would revolutionize the industry and put a power drill within reach of handymen everywhere.
People were happy for, 50 years with an electric drill. But then suddenly they started realizing they were tethered to wherever there was an electrical outlet.
So in 1961, Black & Decker introduced to the world the cordless drill.
They actually just took regular batteries and they looped them together and they used that to power a drill. Had very little power, but it was able to start using batteries instead of cords to do the same kind of drilling. And we progressed in that all the way up to this type of thing. And this is a relatively modern drill.
Today, power drills are the most commonly purchased handheld power tool in the world. They employ drill bits that are made of everything from steel to cobalt, tungsten and titanium. Some even have edges impregnated with diamond dust. And they come in every size and shape imaginable. You can find a drill bit to put a hole through any material. We now return to drilling on Modern Marvels. It's straight out of a science fiction movie, using lasers to vaporize matter. But then again, the next generation of drilling technology got its start from the Star Wars missile defense program.
In the mid-1990s, the Star Wars program was sort of winding down, and some people in the drilling business thought, well, it would be a good idea maybe to experiment with those Star Wars lasers and see if they could be used to drill oil and gas wells. So they went around to the Air Force and the Army and used some of their lasers, and they found that sure, the lasers are powerful enough to destroy rocks or put holes in practically anything. So the idea that Star Wars lasers would be useful was demonstrated, but it was decided that really it was more appropriate to use industrial lasers.
The U.S. government's Argonne National Labs decided to develop the technology.
We found that there are basically three mechanisms for heating rocks with the laser. The first mechanism is when you just put the beam on at a low intensity, the rock temperature rises and it sort of shatters, like what happens if you take a hot glass and you put it in cold water, it's going to shatter. That's the thermal fracture mechanism. If you continue to put the laser beam on for a longer period of time, the rock starts to melt. And if you leave it on long enough, that melted rock starts to boil or vaporize.
To date, Claude Reed and his team have successfully developed the thermal fracturing method. The laser produces an invisible vertical beam the size of a mechanical pencil lead, which shatters the rock fragments. An air nozzle blows the fragments off the surface.
As each layer is removed, then the laser head would go down to the next level, remove the material, then down to the next level. And it just marches downward, step by step, removing each layer of material and taking it out of the hole.
Laser drilling will have several advantages over conventional drilling. It's expected to cost less, work faster, and be more precise. But the technology has a few more hurdles to clear before going out in the field.
In 10 years or more, laser drills could and probably will replace all oil and gas well drilling. There's no real fundamental reason why laser drills can't do that job. They can penetrate any rock material. They can melt and vaporize any material.
On a much smaller scale, laser drills have already proven themselves in other high-tech fields. At DDI Global in Anaheim, California, laser drilling is essential to the manufacture of printed circuit boards, or PCBs.
Without PCBs, you would not have your consumer electronics at home, appliances, could be TVs, computers, cell phones. Just in general, any electronic device today has got a circuit board in it.
Circuit boards consist of anywhere from 2 to 40 or more layers of information conduits, etched on copper film, which is highly conductive of electrical current. Holes are drilled in order to create interconnections between the various layers.
If you took a cell phone board, for example, even just like something like the PDA or the next generation mobile phones, typically in a cell phone today, we have anywhere from 15 to 20,000 holes or greater. And it's just increasing because, again, it comes down to functionality. You want a phone to be your phone, you want a phone to be your email, you want a phone to be your personal friend.
These holes, or microvias as they're called, were traditionally created by devices like this mechanical drill.
The real estate offered on a circuit board is shrinking, so what we're doing is offering smaller holes on the circuit board to make the Z-axis connection. The laser allows us to make much smaller holes than we can with, say, a mechanical drill, and that gives us higher density of the circuit board.
Each flicker of light you see is a hole that has just been created. Using a laser beam results in microscopic holes drilled extremely accurately and at very high speeds.
With our new machine, the EV-CO2 combo, we're doing that at about 2,500 microvias a minute, which is extremely fast.
The laser vaporizes the material that falls in the path of its beam. And not surprisingly, the beam is about to get smaller.
Today we are laser drilling 100 to 125 microns, so we adjust the dash over a human hair. So just looking at it, you can't see it. You got to have very high-powered microscopes to see it. We're talking about going below the human hair. We're going to be going to 50 to 75 microns.
And as we embark on the nanotechnology age, we can only guess at the tiny dimensions laser-drilled holes will assume. No matter the size of the hole, drilling has shaped, or rather reshaped, our world by opening innumerable portals for mankind.
Nie, to już nie fajnie tak było, machanie przy